site visit, everyone will have to get ready, yeah, at 2 p.m. Then we shall leave to maybe earlier, 2 p.m. or 1:45. Then we shall leave to Semenyih, yeah, about 30 minutes from UPM, yeah, and we shall come back before 6 p.m. Okay, so that will happen in week 10. Now week 7, 8, 9, 10. If everything goes well, we shall arrange on the 31st of May. Yeah, but if we cannot meet the requirement or we have problem to arrange for the bus, then I will have to postpone to week 11. But it's okay. I won't disrupt any of other lecture or lab session. Yeah, so the site visit will be conducted during my lecture session. Yeah, so it's compulsory for everyone to join the session. Yeah, and on top of that, yeah, you are the batch with online lab, yeah, and we had never had the opportunity to arrange for a site visit before, yeah, because normally during the third year we shall arrange for a site visit, yeah, to the student. Yeah, unfortunately due to the pandemic, we couldn't make it. Yeah, so hopefully this time around, yeah, at least few of you have the opportunity to visit a water treatment plant. Yeah, but I will keep you posted. Second announcement is regarding on your test, yeah, that will happen on the 12th of May, which is on the day after tomorrow, at 8 p.m. So I need everyone to stand by, to stand by at 7:45, where I will share the link. Yeah, we shall meet at the Google Meet first. Yeah, we shall meet in Google Meet for me to do briefing, yeah, very short briefing. Then hopefully you can start at 8 p.m. You don't have to stay online, yeah, you can stay offline, yeah, but no discussion is allowed. Yeah, this is based on your honesty, and the question also open-ended question. So I believe that you shouldn't discuss. It's going to be a wasting of time. Yeah, if you discuss with your friend, then it's going to be a wasting of time. Yeah, you focus on answering the question. You can always refer to my notes. Yeah, but do not post the question to check. Yeah, do not post the question to check. All right, that's all. Thank you very much, everyone. Now we have 23, meaning to say that one person missing. Okay. All right, we shall start our lecture today with the title of nitrification and denitrification. Yeah, this is an interesting topic because it's related to the previous topic before the semester break, which is on the removal of nitrogen and phosphorus. We have focused more on the nitrogen removal as compared to the phosphorus, because phosphorus I have exposed to you on the techniques of, I think the techniques that we used before is on the chemicals precipitation. Yeah, so let's see what is the biological methods, yeah, that can be used for the removal of nitrogen as well as the BOD. Yeah, okay, mainly all biological treatment has been designed to remove the BOD. It's a part of carbon. Yeah, so if you mention about BOD and COD, they represent the carbon level, yeah, the pollutant load. So but not all, yeah, wastewater treatment plant wastewater treatment technology, yeah, can remove a nitrogen. Yeah, so this is the technology, these are the technology that we are going to explore today. Hopefully we can complete the rotating biological contactors, because before the semester break we have covered on how to evaluate, yeah, the efficiency of a trickling filters. Yeah, so today we shall continue with the rotating biological contactors as well as the design of moving bed bioreactor. Yeah, all right. Um, let me share my slide. Okay, yeah, lecture 7, removal of nitrogen. Yeah. So this is actually a complete loop. Yeah, a complete loop which is required for the removal of nitrogen, which is comprised of nitrification and denitrification process. Okay, is involved two processes, yeah, during nitrification, yeah, which is part 1 and part 2, yeah, the change, the conversion of ammonium into nitrates, and the conversion of nitrates into nitrates, and the conversion of nitrates into nitrogen gases. Then only it can be removed into the air as a part of greenhouse gases. Okay. All right, so let's see. Before we go further, let's see the nitrogen cycle. Yeah, overall, the sources, yeah, the main contribution of nitrogen definitely from the plant as well as the animals. Yeah, so we are not going to discuss in the detail, yeah, about uh, the distribution of nitrogen in soil, because we are more interested on the distribution of nitrogen in water and wastewater bodies, yeah, but mainly the source, yeah, of nitrogen, yeah, from the plant, from the soil, as well as from the animals. Okay, these are the cycle. Yeah, organic nitrogen, yeah, followed by ammonia. Yeah, so this will produce ammonia. Okay, ammonia exists in the form of gases as well as ionic. Then from ammonia, yeah, when it's flow and when nitrogen flow into the water bodies, it will form as ammonia. Yeah, whether it's ammonium gases or ionic as ammonium. Yeah, so normally when we measure for ammonia, we have to measure as soon as possible. Yeah, you know why? Because it exists in the form of ion. Yeah, therefore, if you collect the sample today, yeah, and you measure tomorrow, the concentration of your ammonia doesn't represent the actual condition of your sample anymore. Yeah, so it's good, yeah, if you would like to measure for ammonia, always measure ammonia on the same day, yeah, as soon as possible when you collect the after collection of the sample. Yeah, because you will lose the ammonium ion. Okay, then when it's flow into water or wastewater bodies, yeah, whether in the form of pollutant, in the form of sediment, yeah, it will turns into nitrite. Yeah, so nitrite, this is part of nitrification process, conversion of ammonia into nitrite, as well as conversion of nitrite into nitrates. These two steps are part of nitrification process. Yeah, the process that involve of conversion of ammonia into nitrite with the process of involving oxygen. Yeah, these two processes, ammonia to nitrite, nitrite to nitrates, they involve oxygen. Yeah, oxygen is required, yeah, for the microbes to nitrify the nitrite as well as nitrates. After that, after the conversion of nitrite to nitrates, it will be converted into nitrogen gases. How does it can be converted? It can only be converted through denitrification process. Yeah, denitrification process. In this context, yeah, we are discussing about the use or the roles of microbes, yeah, to denitrify nitrates into nitrogen gas. Then only nitrogen can be released from water bodies. Okay, okay, let's see. Nitrification part 1, yeah, ammonium. Microbes, yeah, microbes which is nitrifying bacteria will consume the oxygen to break down the ammonium that will produce the nitrite plus the energy. Yeah, and part 2 is involved nitrite which has been produced during part 1. Yeah, with the use of oxygen, microbes, these involve different species of microorganism. Yeah, we shall look later what is actually their names. Yeah, the microbes that involved during part 1 as well as part 2. Yeah, so this, but they are known as nitrifying bacteria. Yeah, they use oxygen. Yeah, they are oxygen eaters. Yeah? So they will use oxygen to nitrify the nitrite into nitrate. Yeah? Following this process, yeah, is denitrification process. Yeah? I cannot see that nitrification is more important than denitrification or vice versa. You know why? Because these are a complete cycle. Yeah, this step here is nitrification, and here will be denitrification. It's definitely a complete cycle. It's a continuation process. It's not a reverse process. It's not a reverse process. You know why? Because the nitrates that produce here will be denitrified during denitrification process by denitrifying microorganism. Yeah, but in this process, they don't use oxygen anymore. In this process, they need the helps of waste or food, yeah, to enhance or to stimulate, yeah, the capability of denitrifying bacteria to break down the nitrates into nitrogen gases. Yeah, then only it can be released into the air. Okay. Um, So overall, before I go to the next slide, overall, nitrification part 1 and part 2, is involved or is happen during in aeration, in aerobic condition, aerobic condition. Then denitrification process, since no oxygen involved, is happen in anaerobic condition. Yeah? But between anaerobic and aerobic condition, if you can imagine, especially in water bodies, in a lake, in an open water bodies, the top layer is aerobic layer, because this is the layer with highest concentration of oxygen, the one that can get in contact with the surface water, with the air. Then the second layer after anaerobic layer is known as oxic layer. Oxic layer. After oxic layer is known as anoxic layer. Yeah, oxic layer, the concentration of oxygen is still high, but when it reaches anoxic layer, the concentration of oxygen will be less than 10%. Yeah, so this is where denitrification will occur. And the bottom layer, definitely anaerobic layer with 0% of oxygen. Yeah, okay. So if we can go back to the definition of aerobic and anaerobic condition, we can simply conclude that nitrification part 1 and part 2 is an aerobic process, the process which involve oxygen, while denitrification is an anaerobic process because no oxygen involved. In fact, there needs some food, they need some waste, to further denitrify the nitrates into nitrogen gases. Yeah. Okay. Okay. Why nitrification is so important? Why do I care about nitrification? Yeah. First, we know that nitrification involves two steps of biological process. Yeah, the conversion of ammonium into nitrates and conversion of nitrates conversion of ammonium into nitrates and conversion of nitrates into nitrates. Yeah, that is the process that involve. That is the processes that involve during nitrification process. So why do we care about nitrification? Yeah, because it will affect the ammonia on receiving water with respect to dissolved oxygen concentration. Yeah, because nitrification is important steps to be monitored. Yeah, it has to we have to ensure that it occurs correctly, completely, because it's a loop. Yeah, it's a continuation process. Without nitrification, the system cannot proceed with denitrification. Okay, so that having too much concentration of nitrogen in water bodies definitely will deplete, will reduce the concentration of dissolved oxygen. So this is the problem. Okay, we know that having too much concentration of nitrogen, will affect the dissolved oxygen. Why? Because if we would like to compare between carbonaceous and nitrogenous, BOD, if we would like to compare, Well, if you would like to break down carbon, you will need only one portion of oxygen. Nevertheless, if we would like to break down the nitrogen, we need at least 4 times of oxygen. Yeah, so that indicates, yeah, how fast the nitrogen in water bodies can deplete the dissolved oxygen. Yeah, because bacteria will use 4 times of oxygen if they would like to degrade the nitrogen. Okay. Second, the need to provide nitrogen removal to control eutrophication. Okay, nitrogen is one of the parameters that can contribute to eutrophication, but honestly, they are not the limiting parameters. You know why? Because the limiting parameters for nitrification is phosphorus. Yeah, at correct ratio of nitrogen and phosphorus, at correct ratio of nitrogen and phosphorus, then only eutrophication will occur. Yeah, so yeah, we need to control the nitrogen, but the main issue is more on dissolved oxygen depletion, and not exactly on eutrophication. Yeah, because the limiting parameters is not nitrogen. The limiting parameters that can lead to eutrophication is phosphorus. Yeah. Okay, and the need to provide nitrogen control for water use, especially for the groundwater application. So these are the reason why nitrification is important and need to be monitored. Yeah. So overall, since it's a loop, it's a continuation process, we have to ensure that both nitrification and denitrification process occurs accordingly. This allow the nitrogen to be released from water bodies. Yeah, so these are the discussion, on the source of nitrogen that enters a wastewater stream in the forms of ammonia, in the form of urea from the urine, and also the organic nitrogen. Okay, so normally in lab, if we would like to measure the concentration of nitrogen, we don't have to, if we already have the data on the concentration of protein, so that we don't have to further measure the nitrogen, because 62% of the protein is nitrogen. Yeah, so normally when I send my sample to the analytical lab, they will, and I would like to know the both protein and nitrogen, they will only measure for the protein. Yeah, and they will give me the data both protein and nitrogen. How? Because 62% of the protein is nitrogen. Same goes to ammonia. Yeah, ammonia also is a part of the nitrogen. Okay, on top of that, from in wastewater treatment plant, most of the contributors of nitrogen are from our urine, the waste, and also small portion of the fertilizer. As compared to the marine environment, the contribution is more on the untreated wastewater, livestock wastewater, as well as fertilizer. Yeah, so if you are to compare the concentration of nitrogen in wastewater, livestock wastewater is contain the highest concentration of nitrogen as compared to other types of wastewater. Yeah, uh, I'm talking about organic nitrogen lah. If you are talking about inorganic nitrogen, then definitely industrial wastewater contain higher concentration of nitrogen. Yeah, but if you are looking from the point of view of organic nitrogen, then livestock wastewater is the toughest waste to deal with, because they contain high nitrogen level. Okay, so these are the names, the one that I promised just now, the names of the microorganism that involved. The first steps, the microbes that involved during part 1 of nitrification is known as nitrosomonas. Yeah, is also, and these are the major microbes, and it can also exist as nitrosococcus and nitrospira. Yeah, So during the second step of the nitrification is involve nitrobacter. Yeah, nitrobacter, which convert from nitrate to nitrates. Yeah, nitrates. Yeah, NO3. Just now NO2 kan? Yeah. Okay. So these are the major water qualities problem associated with nitrification. You know why? In in layman in layman term, how do I explain nitrification is the process of the uh, converting of the nitrogen from one phase to the other phase. Yeah, but it doesn't remove the nitrogen at all. That's why denitrification is required. Yeah, but in order to allow denitrification to occur, the water bodies has to complete these two processes. Yeah, nitrification part 1 and nitrification part 2. Why? Because in the form of nitrates, then only it can be converted into nitrogen gases, then can be released into the air. Okay. All right. So nitrogen exists in the form of five major forms. The first one is organic nitrogen, ammonia, nitrite, nitrates, and dissolved nitrogen gas. Okay. There are few techniques that can be used for the measurement of nitrogen. Yeah. The first one is Caldar nitrogen. This the machine. Is if I'm not mistaken, this is a German name. Caldar nitrogen is an equipment that normally being used after the scientists who first suggested the analytical procedure. So we normally use this. This is a titration method. But before we can titrate the sample, we have to conduct acid digestion. Yeah, we have to conduct acid digestion with the addition of nitric acid, sulfuric acid, and together with your sample, then we can break down all the substances that contain nitrogen. Then only we can start it with titration. Yeah, titration using this machine. Okay, so these are the machine to be used to measure for nitrogen. On top of that, nitrogen can also be measured as nitrite or nitrates. Yeah, it can also be measured as nitrite or nitrates. Yeah, so normally the machine that can be used to measure nitrite or nitrate, which includes liquid chromatography, ion chromatography, HPLC. Yeah, so these are the machine that can be used, but they are being measured in the form of ion. So normally, if we declare as total nitrogen, so we put in bracket as nitrate and nitrite. Yeah, because we have to declare they were measured in the form of ion instead of in the forms of total nitrogen. So the correct method to be used to determine the total nitrogen, you have to use this machine. Yeah, but the quickest way is to use analytical machine. Yeah, because this machine to use this machine, you have to conduct acid digestion goes to phosphorus, but the quickest one is by using analytical equipment. Yeah, ion chromatography or liquid chromatography. Okay. Um, Okay, most widely used method is the biological nitrification and denitrification process. So, nitrification is considered as autotrophic process. Why? Because it's related to organism converting sunlight to into energy. Okay, so these are the example. Yeah, of the movement of nitrification involved in a plant and soil. In fact, they have been using the few machine learning algorithm. They have been using the kinetic study to monitor the movement of nitrogen in soil and how does it relate to the growth of the plant. Yeah, I think I noticed one journal paper which has been published in the top 10% journal recently by one of UPM researcher. So she has been monitoring the nitrogen, yeah, the nitrogen recycle between the plant as well as the soil. Okay, so this is what I meant before. CBOD and NBOD. We have two types, carbon BOD as well as nitrogen BOD. Yeah. So dealing with carbon BOD is fine because it's involved only one portion of oxygen. However, when you are dealing with nitrogenous BOD, it's involved 4 times of oxygen. So the calculation below is how do we reach to the conclusion, that um, every one portion of NBOD, nitrogenous BOD, will require 4.57 gram of oxygen. Okay, so this is how that we come to the conclusion. Okay, we shall use this value later when we are to design the moving bed bioreactor for a combined BOD as well as nitrification process. But the steps are more or less are the same. The only difference is whenever you would like to remove for the nitrogen, you have to use 4 times the value of the oxygen. Okay. So these are the steps just now: nitrosomonas, the conversion of ammonium into nitrite. Yeah. Then these are the conversion of the nitrite into nitrates. Yeah, involve nitrobacter. Yeah. Overall, you have to memorize this equation, but it's no longer a problem. Uh, yeah, but depends on the instruction by the university. As far as I'm concerned, your final exam will be a face-to-face exam, so you have to memorize this equation. Okay, so nitrosomonas, and nitrobacter, both microbes which exist in first part and second part of nitrification, use energy from this equation for cell growth as well as the maintenance. Yeah. So these are the design calculation which you have seen before. Yeah. So next is on denitrification process. Okay, denitrification process is a process where conversion of microbes will use the waste, the food just now, to convert the nitrates into nitrogen gases. Yeah. So the names of the anaerobic bacteria that involve, facultative and anaerobic bacteria that involve during this stage is pseudomonas. Yeah. So this nitrification requires source of carbon. Yeah. That's why in order to proceed with the denitrification process, they don't want oxygen. Sorry. Okay, they are not oxygen eaters. Yeah. So you have to supply them with the food, enough food, enough waste in case that there is no food available. So methanol can be used, to the replacement of the carbon source, so that then only the nitrate can be converted into nitrogen gases, during denitrification process. Okay, in denitrifying microbes, is require very low concentration of oxygen. That's why I said just now is require environment with less than 10%, where in this case, a noxic environment is the best, is the best environment, to be used, in order to provide a good environment for denitrifying process. Okay, let me draw. Yeah. So this is, you can imagine, this is water bodies. Yeah. So the top layer, is known as a, did I spell correctly? Aerobic process. Yeah. This is aerobic condition. Yeah. Aerobic condition. Then the next layer is known as oxic. Yeah. So normally nitrification will occur during in this layer. The next layer is known as anoxic. And denitrification will occur at this layer, and the bottom layer is known as anaerobic. Okay, anaerobic layer. Yeah. So the lowest the position, the less will be the oxygen. Okay, at this level already less than 10%. Yeah, anoxic already less than 10%. This can be 0 to 1%. Okay, so the area that we are interested today is these two layers. Yeah, if you can imagine for water bodies, then nitrification will occur in oxic layer, while denitrification will occur in anoxic layer, where oxygen should be less than 10%. Okay, so the bottom layer is anaerobic layer. So anaerobic layer is the oxygen concentration is between 0 to 1%. Okay, all right. Okay, these are the combination. Yeah, if we are to compare between the process, these are the combination, simultaneous nitrification and denitrification. If we can imagine, for an oxic layer, nitrification will occur. Yeah, for in anoxic layer, denitrification will occur. So these are the relationship between these two processes, because they are not a reverse process. They are a continuation process. It's a continuation process. If we cannot complete nitrification, then denitrification cannot be conducted. Because why? Because during denitrification process, definitely they are waiting for this nitrate. They are waiting for this nitrate, which is produced during nitrification process. Okay, so these figures, the one that I simply draw just now, you can imagine for a pond or lake, because the environment exists at different layer. This is a natural water bodies. But if you are talking about the wastewater treatment plant, they definitely will provide a specific place, so that they can preserve the anoxic zone. So this is the zone where oxygen less than 10%. So this is an open area. So this is an open area where it's known as oxic zone. Okay. All right, next is on nitrogen removal process. Before I go further, we are going to do the design. We are going to proceed with the design of RBC. Before I can proceed with the design of RBC, I think maybe you can watch a video on nitrification process. It's a very good video, about 10 minutes. 10 minutes video.
Hi, this is a guide to using elements in Genshin Impact. For example, Pyro can help to defeat Hydro slimes and even to light up fires. Hydro helps you easily fight and destroy Pyro mobs, and you can defeat strong bosses with it. Anemo will help you to fly.
Okay, happy watching.
Much like carbon, nitrogen follows a basic pathway in a continuous cycle. This cycle is critical to all living organisms that have existed or will exist on the planet. Wastewater treatment plants play a critical role in reintroducing nitrogen back into this cycle with limited environmental impact. High levels of nitrogen entering natural waterways can result in toxic conditions for wildlife, dissolved oxygen depletion, and excessive algae growth, all harmful to local plant, animal, and human populations. Nitrogen enters wastewater through various pathways. The most abundant contributor of nitrogen in typical municipal wastewater is urea. Yeah, urine. Other contributors of nitrogen are food processing waste, chemical cleaning agents, and many other industrial components. Nitrogen is present in wastewater in various forms, which have been lumped into separate general categories. Nitrogen in the form of ammonia is ammonia nitrogen. There is also nitrite nitrogen and nitrate nitrogen, which are usually formed during the actual biological processes at the wastewater treatment plant. In addition to these forms, nitrogen makes up a small percentage of the cell mass of the organisms in the system, as well as other dissolved organic compounds. This category is referred to as organic nitrogen, of which a certain amount typically cannot be removed through the biological processes that will be described in this video. Total nitrogen, as the name implies, is the sum of all types of nitrogen. TKN, or total Kjeldahl nitrogen, named after the scientist Johan Kjeldahl, is the sum of only organic nitrogen and ammonia nitrogen. TIN, or total inorganic nitrogen, is just as the name implies, the total nitrogen minus the organic nitrogen. In simplistic terms, nitrogen in various forms is flushed, rinsed, or otherwise introduced into the sewer system. Almost all of this organic nitrogen, urea for example, is immediately hydrolyzed into ammonia. In water, gaseous ammonia, NH3, is almost entirely converted to ionized ammonia, or ammonium, NH4+. Specialized autotrophic bacteria, or nitrifiers, convert the ammonium to nitrite, NO2, and then to nitrate, NO3, through various biological processes. As dissolved oxygen is depleted by the nitrifiers and other organisms in the basin, other specialized heterotrophic bacteria, denitrifiers, are able to thrive by using the oxygen attached to the nitrate molecules for respiration, creating nitrogen gas as a byproduct. The nitrogen gas then simply bubbles out of the water into the atmosphere. Pretty slick, right? Well, let's go back to the beginning and take a closer look at each of these important steps in the nitrogen removal process. First, as a natural reaction in an aqueous solution, or in water, the vast majority of the organic nitrogen immediately hydrolyzes into ammonia. Most of this ammonia automatically converts to the ionic form ammonium. The equilibrium between the gaseous and ionic forms of ammonia is heavily impacted by the pH of the water. A more acidic solution will favor the ionic form ammonium. A more basic will favor the gaseous form ammonia. Since wastewater typically ranges between a pH of 6 and 9, almost all of the ammonia will be in the ionic form. Since ammonia testing accounts for both forms, ionic and gaseous, it is not necessary to worry about each form separately. No bacteria is necessary for this conversion, it just happens. The next step in the process consists of converting ammonium to nitrite and then nitrate. This two-step process is usually lumped into one term, nitrification. This step is facilitated by a specialized autotrophic bacteria. So what does autotrophic mean? There are two broad categories for how organisms obtain carbon required for growth, autotrophs and heterotrophs. Autotrophs are able to obtain their carbon from non-organic sources, such as carbon dioxide and the alkaline bicarbonate. Plants are good examples of how this is done. Heterotrophs, on the other hand, require organic sources of carbon. Essentially, heterotrophs get carbon by consuming other organic compounds, humans and animals being good examples. In contrast to heterotrophic BOD-consuming bacteria, autotrophic nitrifiers require more time to mature and maintain their population in a biological wastewater treatment system. The nitrifiers dictate the SRT in nitrogen-reducing plants. How fast nitrifiers grow depends on the temperature of the wastewater and the amount of dissolved oxygen present. If nitrifiers aren't allowed enough time to thrive, you run the risk of accidentally wasting them out of the system entirely and losing nitrification. Higher temperatures and DO concentrations means faster growth. Colder temperatures and lower DO concentrations means slower growth. Also, when no DO is present, nitrifiers can become completely inactive. As a note, it is important to remember that nitrifiers are also quite sensitive to pH, tending to function most comfortably in water with a pH between 6.8 and 7.5. Once a healthy population of nitrifiers has developed in your system, the first step, performed largely by a group of bugs known as ammonia oxidizers, will take the ammonium and DO and convert it into acid, water, nitrite, and energy. If your system doesn't have adequate alkalinity, the acid produced here could create inhospitably acidic conditions for the bacteria, resulting in major process hiccups, including loss of nitrification. The water produced is absorbed in the system, the nitrate moves on to the next step, and the energy is used by the bacteria to grow and multiply. The second step, for which a group of bugs known as nitrite oxidizers is largely responsible, takes that nitrite and more DO and converts it into nitrate and energy. This conversion from ammonia to nitrate is nitrification. Typically, full nitrification is observed when ammonia concentrations are reduced to less than 2 milligrams per liter and nitrite concentrations to less than half a milligram per liter. As mentioned, nitrification is a very oxygen-hungry process. As a comparison, in order to remove 1 pound of BOD, 1.2 pounds of oxygen are required. However, to reduce 1 pound of ammonia to nitrate, 4.6 pounds of oxygen are required. Since getting dissolved oxygen into wastewater is a very energy-intensive process, it would benefit every treatment plant's electrical bill if they didn't aerate more than they needed to. Over-aerating does nothing to improve the process. It really is flushing money down the toilet. After nitrification, the nitrogen is still in the system, mostly as part of the bugs and in the form of nitrate. Though not as toxic as ammonia, nitrates can still contribute to eutrophication and if released into a source supplying drinking water, can endanger human populations, specifically infants, causing what is known as blue baby syndrome by interfering with blood oxygenation. The final step in completely removing nitrogen from the system is called denitrification. Since nitrification is converting ammonia to nitrate, one could think that denitrification is simply the reversal of this process. Confusingly, yet fortunately, this is not the case. Denitrification is performed by a specialized heterotrophic bacteria. These guys require some pretty specific conditions to perform this step. First of all, they need some food, or BOD. In order to oxidize that food, they need oxygen. Their easiest and first choice for oxygen is DO. If there is no DO present, however, they look to alternative sources, such as nitrate. These specialists have the ability to strip the oxygen from nitrate molecules to satisfy their needs. This critical environment where DO is not present, yet nitrates are, is referred to as anoxic, and is absolutely required for denitrification. These bugs take the BOD and nitrate to produce energy, base, and nitrogen gas. The base is actually very useful in buffering the acid produced during nitrification. The nitrogen gas then floats in tiny bubbles to the surface and into the atmosphere. Though great in the biological basin, denitrification in a clarifier can result in undesirable floating sludge. There are many alternative strategies for developing anoxic conditions. Some treatment plants are designed to have dedicated anoxic zone volumes in the flowchart, while others strive to develop these anoxic zones within the oxidation ditch or aeration zone by rigidly controlling aeration or by turning off aerators for set periods of time. Additionally, under certain conditions, microanoxic zones can be developed within the bacterial flux themselves, resulting in what is referred to as simultaneous nitrification-denitrification. Various levels of denitrification may be required depending on the local discharge permit. However, full biological denitrification typically results in only 1 to 3 milligrams of nitrate in the effluent stream. Now, let's take a look at some real-life operational scenarios. During your routine operational sampling, you notice that the ammonia in the effluent is beginning to rise above 1 to 2 milligrams per liter. Let's think about what could be causing this. We know that nitrification is an oxygen-hungry process. Perhaps the aeration is insufficient. We also know that nitrifiers grow more slowly. Perhaps the SRT is too short due to an influence of temperature. Also, we know that nitrifiers are very sensitive to changes in pH or toxic conditions. Perhaps this performance loss is due to a disturbance of that nature. Knowing these things, the possible solutions are easily determined. If low DO is the culprit, full nitrification will return by increasing aeration. If temperatures have dropped, the SRT may need to be increased to maintain a healthy nitrifying population. If pH or toxicity is the culprit, certain specific actions may be required depending on the exact cause. For the next problem, instead of ammonia, you notice that your effluent nitrate concentration is on the rise. What could cause this to happen? Well, we know that denitrification requires anoxic conditions be formed in the basin. Perhaps these conditions are not being allowed to develop due to over-aeration. A more unlikely yet possible cause could be lower than usual BOD in the influent. If anoxic conditions are not being allowed to develop due to too much DO, decreasing the aeration will help in restoring these special conditions. If the BOD loading is unusually low, there may not be enough carbon for the denitrifying bacteria to perform. This less likely scenario would require additional carbon be added to the influent stream. Finally, during your afternoon stroll through the plant, you notice unsightly small bits of floating sludge accumulating on the surface of the clarifier. Upon this discovery, you immediately remember this helpful video discussing this exact scenario. It becomes obvious to you that your sludge blanket at the bottom of the clarifier is going anoxic and denitrifying, causing sludge to float due to the generation of nitrogen bubbles. Letting instinct take over, you spring to action by increasing the recycle rate, thus reducing the sludge inventory time in the clarifier, preventing this unwelcome denitrification. So in summary, a wastewater treatment plant helps nitrogen through the nitrogen cycle by optimizing conditions for nitrification and denitrification. By so doing, wastewater treatment plants help minimize the human impact on our fresh waterways and environment.
Okay, right. Okay, now we have completed the video. A very good video.
Look at this. If low fixed deposit.
Okay, a very good video on nitrification and denitrification process, and I hope the video has further clarified, improve your understanding. All right, so we are into the design for the two system. We have today we are going to cover two system because before the semester break, we have discussed about trickling filters, which is another treatment process which can be used to remove both BOD as well as nitrogen. Okay, so today we are going into detailed calculation on the rotating biological contactors as well as moving bed bioreactors. Because these two systems, they are very good. For these two systems, I mean trickling filters as well as the moving bed bioreactor, they are very good for the removal of nitrogen as well as the BOD. But for RBC, RBC can also be used for the removal of nitrogen, but they are mainly being designed for the removal of BOD, or carbon. Okay, so let's see the example of the calculation. The example of the calculation for moving bed bioreactor is available in your slide, but the example for the calculation of the rotating biological contactors is not available in your slide, but available in a separate reference, which is oh dear. Okay, this one we have covered before the semester break. Okay, I'm going to close this one. Okay, next, we are going to discuss about the design of rotating biological contactors. Let me clean this up. Let me clean the whiteboard first. Because I teach the other student. On the design of RBC previously. Okay, this is rotating biological contactors. Okay, if you still remember, during design or the evaluation of trickling filters before the semester break, we have focused on the nitrogen as well as BOD, So for the RBC, we are focusing more on the BOD rather than nitrogen. Even though the system also good for the removal of nitrogen. So this is example 1, lecture 7. A staggered RBC design for BOD removal. Given the following design condition, so develop a process designed for a staggered RBC system. So in this case, background noise. 1 second. Okay. Okay, so for the primary effluent, the flow rate given to here is 4,000 meter cube per day. The BOD is 150, the BOD is 150, 140. The SBOD is 90. Okay, what is the difference between BOD and SBOD? Okay, BOD is equal to S naught. But is this? They are the raw concentration of BOD in your sample. they are the real concentration of BOD in your raw sample. Yeah. But if you are talking about SBOD, okay, S here stand for the word soluble. Okay, soluble BOD in many cases, and it has to be less than BOD. So in this case, you can see that the real BOD is 140. The real BOD for the sample is 140, while the soluble BOD is only 90%. Based from my previous experience, normally the soluble BOD is about 60%. 60% of the real BOD. So we are actually now measuring in the same sample, but the method is different. Okay, what is the difference? If you are measuring the BOD or S node, you simply take your sample and measure for the biochemical oxygen demand. Nevertheless, if you would like to measure for soluble BOD, normally you have to centrifuge your sample. You have to centrifuge your sample, or you have to filter your sample. So only take the supernatant. When you only take the supernatant for the measurement of the BOD, that will give you the reading of soluble BOD and not the actual BOD. Okay. Alright, so you are also given the value of total suspended solid. So you have to be careful. This question asks you to design for BOD removal. If you are being asked to design for nitrogen removal or TSS removal, then in the following calculation, you should use the value of nitrogen or total suspended solid. Okay, first, this is a long calculation. My advice is for you to be careful, to follow one by one the step. Okay, given the first stage of the SBOD, where did I get this value? So I got this value from here. Okay, table 9.8 also will be provided to you. The first stage of organic loading. In this case, the value that we use in our example is 15 gram per meter squared day. 15 gram. So in this appendix, the suggested value is between 12 to 15. Okay, 12 to 15. So you can use any of the value, whether 12, 13, 14 or 15, unless the question stated that design for the maximum, then definitely you have to use 15 lah, or design for the minimum, then you have to use 12. So in this case, you are going to start your calculation with the SBOD. SBOD. So SBOD is going to be this value. This value. Okay, 12 to 15. Okay. The next one, so in this example, I take as 15. Okay, calculate the SBOD loading. So SBOD loading, so S just now is equal to 19 times 4,000. The flow rate is given, then you will get the BOD loading in gram per day. Then you calculate the this area. Okay, this is where that you need to use the value of 15. Okay, so this area is equal to SBOD loading, divided by the first stage SBOD. So you will get this area equal to 24,000 meters squared. Okay. See, given the shaft area, which one is the shaft area? Shaft area is this one, the one in red here is the shaft area. So this is on manufacturer standard. So normally we will be using this value, but depends on the manufacturer guideline, the specification. So in this case we use 9300. Okay, now we are projecting, what are we actually doing? We are projecting the size of the RBC required, the size of the RBC required based on the SBOD loading. Okay, so we know that the per shaft, area per shaft is 9,300. For that reason, based on the area required, where do we get the area? The area was was derived, the area was derived from the SBOD loading. So that's why we use the area divided by the shaft area, the area per shaft. So in this case, the answer is 2.6. So 2.6 normally we take as 3 lah. As long as it's more than 2, then we will take as 3. So we can conclude here that the system require 3 shaft. Okay, 3 shaft. Okay, so the word is 3 shaft. Okay, 3 shaft. What do I mean by 3 shaft? 1, 2, 3. These are 3 shaft. Okay, first you must be careful. These are the keywords. Train is always equal to the number of shaft. Okay, so in this case, this is shaft number 1, shaft number 2, shaft number 3. Okay, so in this case, we have first train, we have second train, and we have the third row will be the third train. So train and shaft will be moving in a row. So the one that we are not sure here, because train is equal to number of shaft. Whenever you calculate number of shaft is 4, then there will be 4 train here. Why? Because train moving in a row. So in this case, the one that we are not sure is the number of stages. What do I mean by number of stages? Number of stages is the one that move in the forms of in column. The one that move in column, which is in this case is use another colors. Orange. Okay, in this case, the one that move in column is known as stage. Okay, stage. So we are not sure yet how many stages. In this case, we just assume 3 stages. But we are not sure whether 3 stages is sufficient. For us to treat the wastewater. How do we know it's sufficient or not? Because in the question, it's already stated the target effluent. That's why we can determine whether the number of stages provided is sufficient or not. Okay, first you need to make the assumption. The first assumption is 3 stages as well as 3 train. 3 train is okay, but 3 stages we are not sure yet. This is still unknown. So how to confirm this? First you need to calculate the flow rate divided by the train. Okay, 4,000 divided by the numbers of train. So the numbers of train, 4,000 is the flow rate, flow rate divided by the train, and the train is the one that moving by row just now. Moving by row, the train. So that you have 3 trains. So 4,000 is the given flow rate divided by 3. So you will get 1333.3 meter cube per day. Okay, next you have to use this formula. Okay, this is a fixed formula. I will provide to you the solve of this formula. So there are so many constant we have been set in this formula. The only value that you have to change is AS over Q and S naught, AS over Q at the bottom. Okay, so how do you change this? First you calculate for S1, stage 1. So whenever you calculate for stage 1, you have to substitute the value of S naught. Okay, so what is the value of S naught? The value of S naught is given as 90. So you substitute into this equation as 90. The rest fixed. Value 1, -1, 4, 0.00974, 2, 0.00974 fixed. Okay, then AS over Q. How to calculate AS over Q? AS is given as 9,300 divided by Q. Q is this one just now. Okay, then we get 6.97. Okay, now I want everybody to calculate. To calculate, to check whether you can get this value or not. Whether the one that I have calculated earlier is correct or not. Okay, so you are now calculating for the S1. Bear in mind, so you have to use the value of 90 to substitute into this formula. Okay, 5 minutes, calculate. Okay, did you manage to get 29.8?
Yes.
Okay, great. Okay, next, yeah, I want you to calculate for S2. Yeah, whenever you would like to calculate for S2, you have to use the value of S1. You have to substitute the value of S1 into this formula. Okay, see, whenever we calculate for S1, we use S naught. So if you would like to calculate for S2, meaning to say that you have to substitute the value of S1 here. Okay, so now you start with the calculation.
Dapat 14.8.
Okay, great. Next, you can calculate for S3. So whenever you calculate for S3, you use S2. Okay.
Get the same, like 9.13. So round will be like 9.1.
Okay, great. Yeah. So when do you know? How do you know that you have to stop? Okay. You know that you have to stop whenever your final value here is less than 10. Yeah. Where do I get 10? 10 is from here. Yeah, the target effluent. Yeah, the target effluent concentration for the SBOD, yeah, is uh, for the SBOD is 10. Yeah, so that whenever you got the value less than 9.1, so that since the goal was 10 for S3, then the proposed design is satisfactory. Yeah, until you got less than the target effluent, then only you can stop. Okay, after that, any question?
Noted.
Alright, great. Alright, next is to determine the first stage organic loading. Okay, how to determine the first stage organic loading? We need the value of flow rate, which is the F, yeah, times the value of the soluble BOD, which is 90. This is SBOD, yeah, SBOD, the soluble BOD, divided by number of stages, which is 3 times AS, yeah, the area of the shaft just now. So you will get this value. Then you have to calculate the overall organic loading. So the difference is whenever we calculate the overall organic loading, yeah, we have to use the value of the real BOD, yeah, not the soluble BOD, which is in this case is 140. Yeah, then divided by the stages, by the number of shaft, yeah, as well as the area. Yeah, the unit is still the same. You know why? Because this, even though the previous one, yeah, even though the first stage organic loading, it's only involved the number of stages, yeah, but uh, because they are dimensionless, they have no unit. So in this, to calculate the overall organic loading, yeah, we have to consider the number of stages as well as the number of shaft, yeah, so that there is no difference in terms of unit, yeah. And the last one is hydraulics loading. And to calculate the hydraulics loading, you need the flow rate divided by number of stages, number of shaft, as well as the area. Okay, any question?
No, Doctor.
Okay, good. Alright, next we can proceed to the design of moving bed bioreactor. Okay, so these are the the trickling filters as well as the rotating biological contactors. Yeah, so we have evaluated the performance of trickling filters before the semester break, and today we have completed the design of the rotating biological contactors. Yeah, so these are the recommended loading rate for the trickling filters. Yeah, with the media. Yeah, because these are the attached growth system. Yeah, the attached growth system are the system with the media. Yeah, if you can revise, if you can recall a little bit, how does the system work? For the rotating for the trickling filters, this is the only this is the only system that they have. That's why they always introduce the recirculation. Yeah, as compared to the RBC, one shaft is not sufficient, and that's why we have to know based on the loading or the wastewater that we would like to treat, what is actually the actual numbers required. Yeah, to achieve the target effluent. Yeah, but for trickling filters, only one unit is sufficient, but they always employ the recirculation. Yeah, so that they can further remove the waste. Okay. Next one is moving bed bioreactor. Okay, maybe we can spend 1 or 2 minutes to watch the video on MBBR. Yeah. I think we already watched the video maybe.
Before we were using Monday.com, our team was drowning in work. Our days used to split between work.
With the MBBR process, operators can maximize treatment capacity while minimizing their footprint. An MBBR system is a fraction of the size of a conventional system and can be built without the need for a return-activated sludge stream, allowing for a single-pass process. Additionally, the Headworks Bio MBBR biofilm process is self-regulating, automatically responding to fluctuating organic loads without the need for operational adjustments. Headworks will work with your consultant to customize your MBBR system, configuring your new plant for the applications your discharge permit requires. Full treatment of municipal wastewater, industrial wastewater, or treating wastewater for reuse. Also, standalone pre-treatment or post-treatment reactors can be used with existing systems. Let's walk through an example of the MBBR process designed for total nitrogen removal. To begin the MBBR process, influent from the headworks passes through a fine screen and enters the treatment system. Free-flowing biocarriers are distributed throughout individual reactors, and effluent screens act as sieves to keep the biocarriers within each specific reactor. A mechanically mixed anoxic reactor combines the influent stream with a recycle stream from the nitrification reactor. At this point, nitrogen is released into the atmosphere in a process called denitrification. The next reactor is for BOD and/or COD reduction and requires approximately 2 to 3 hours HRT. The high level of carbon food source in the influent stream maintains a rich concentration of heterotrophic bacteria living on the biofilm, which is required for BOD reduction. In the third reactor, the influent has low levels of BOD, limiting the growth of heterotrophic bacteria, and contains high levels of ammonia, supporting the growth of autotrophic bacteria on the biofilm required for nitrification. The nitrification process oxidizes ammonia to nitrates and nitrites in order to meet the required discharge levels. After the MBBR process is complete, clarification removes suspended solids from the treated wastewater. At this point, the effluent is ready for any optional tertiary treatment. The Headworks Bio MBBR aeration and mixing processes produce a continuous sloughing rate, which maintains a more active biofilm. Treatment capacity can easily be expanded by increasing the fill fraction of the biocarriers within the reactor, as much as 70% by volume. At equal levels of BOD removal, Headworks Bio's MBBR provides up to 5 times the biofilm surface area of a trickling filter, using less than a quarter of the reactor volume. When compared to an activated sludge extended air process, MBBR saves time as well as tank space. Whereas activated sludge is designed for 12 to 24 hours of hydraulic retention time, MBBR needs only 2 to 3 hours to achieve the same level of nitrification, using a quarter or less of the tank volume. Headworks Bio has designed and implemented MBBR installations for municipal and industrial applications for 15 years, including resorts, cruise ships, food processors, power plants, and petrochemical plants. If you're building a new treatment plant, Headworks Bio can provide an MBBR solution to meet your capacity and treatment requirements.
Okay, so these are the MBBR. MBBR, which is moving bed
The world is
bio
entering into an economic recession.
bio
Market volatility is at an all-time
bioreactor.
high.
Okay, so let's see the design calculation. Okay. We are going to design the moving bed bioreactor. There are 2 sections. The first section is on the sizing of the system, on the sizing of the filter media, on the capacity of the filter media. The second section is on the volume of oxygen required. Yeah. Why do I say that? Because this system is an aerobic system where we have to supply the oxygen, thus allow the filter media to keep floating within the tank. Yeah. So this involves both for BOD removal as well as nitrification process. Yeah. So maybe we don't have. Maybe we are going to cover first part, which is the design on the sizing of the tank as well as the filter media. The section for the calculation of the oxygen required, will be continued next week. Moving bed bioreactor. Okay, moving bed bioreactor comprise of primary clarifier. First tank, it can be BOD removal or nitrification removal, nitrogen removal. The second tank will be the nitrification in this case. Yeah. So sometimes it can involve only one stage MBBR process, which is only one tank involved, which is for BOD removal. But we can also incorporate, we can also integrate another tank for the further nitrification, nitrogen removal, which is the nitrification tank. So the final tank in the MBBR process is known as secondary clarifier. So secondary clarifier are the final tank, which is required, for the sludge to settle after the biological process that occurs both in the BOD removal tank as well as nitrification tank. Okay, so you have to look at this carefully. First, we have primary clarifier. For all design of wastewater treatment plant, we know that during primary clarifier, the BOD should have been removed about 30%. 30%. As we designed previously, in a conventional activated sludge process. So the remaining 70%, only remaining 70% of the BOD are going to be treated during biological treatment, which is in this case is MBBR system. It's a combined removal of BOD as well as nitrogen. Okay, you can see at the bottom that we have air that being supplied both to the BOD removal tank as well as nitrification tank. Okay, first we are going to do the sizing for the BOD removal. How to do the sizing? BOD loading rate in gram per day equal, you need to calculate for BOD loading rate. How to calculate for the BOD loading rate? Flow rate times BOD concentration. We have calculated before last time that when we would like to calculate for the area, so BOD concentration. And number two, we need to calculate for the carrier surface area. Carrier surface area is the filter media. So BOD loading, the one that we have calculated before, divided by the surface aeration loading rate. SALR stand for surface aeration loading rate. I will, before I upload this note in Putra Blast, I will include the full term for SALR. So where can we get the value of SALR? Typical design for MBBR reactor, the value for the surface aeration loading rate is equal to 6, where it can remove about 90 to 95% of the BOD. Next, sizing, and next is a continuation. Number 3, we have to calculate the volume of the media. So the volume of the media equal to carrier surface area. Carrier surface area. Where do we get carrier surface area? From number 2. Carrier surface area divided by media specific surface. So media specific surface normally is available from the manufacturer. So in this case, the specific surface area for these types of media is 500. So number 4, calculate the volume of the tank. Volume of the tank equal to media volume divided by fill fraction. What is fill fraction? Fill fraction is the area or the volume of the water tank which has been loaded with the filter media. I repeat, fill fraction is the volume of the wastewater tank which has been loaded with the filter media here. So typically around 30 to 70%. But normally we will, my previous experience, we use about 40 to 50% of the working volume. Okay, we put, let's say the working volume is 3 liters, then we put 1.5 liters of the filter media, because this one is very small. The diameter is about 1 centimeter only. The diameter of the filter media, very small. Okay, next, first, just now we have calculated, and this is the sizing for the BOD removal tank, which is this one, BOD removal tank. Next, we are going to do the sizing for the nitrification tanks. Okay, sizing for nitrification tank. First, we have to calculate the nitrates loading rate, same with the BOD just now. So flow rate times concentration of the nitrogen, ammonium nitrogen. Then you calculate the carrier surface area. Same step, but you need to use the value of surface aeration loading rate. So in this case, for nitrogen, if you would like the effluent concentration of ammonia in your sample more than 3 milligram per liter, then the design for the value for the SALR is equal to 1. Nevertheless, if is less than 3 milligram per liter, depends on how stringent the regulation. Okay, if you would like to design for the effluent less than 3 milligram per liter, for this reason, the design of SALR is equal to 0.45. Then after that, you can start with the sizing. Media volume equal to carrier surface area divided by media specific surface. Same. Carrier surface area you got from number 2, media specific area from the manufacturer. The same, the same. This one, the same types of filter media, which is the specific area is equal to 500. Okay. Next, you can calculate the volume of the tank for nitrification tank, which is media volume divided by the field fraction. Yeah, don't forget to allow the freeboard. Yeah, the excess the excess head loss. Yeah, so that in the tank, so that we can allow some head space. Yeah, so just now for the BOD removal is about 0.35. Same goes for the nitrification, also about 0.35. Okay, let's try the example. Okay, design a two stages, yeah, moving bioreactor secondary treatment system, yeah, for a flow of 10 meter cube per day, considering initial BOD equal to 250 milligram per liter. Yeah, the initial BOD equal to 250 milligram per liter, yeah, given to you, and the required effluent BOD, yeah, is 10 milligram per liter. Okay, and also you also need to consider on the designing of nitrification tank, where the original concentration, considering entering, yeah, the entering ammonia nitrogen is equal to 40 milligram per liter, and the required effluent is equal to 4 milligram per liter. Yeah, so first you just follow step by step, yeah, as presented before. So you are going to do the sizing for the BOD removal tank. Yeah, so BOD loading rate is equal to assuming 30%, yeah, of the BOD removal in septic tank. Yeah, 30% of the BOD removal in septic tank. So as I mentioned to you, yeah, not only in septic tank, also in the secondary tank, yeah, during preliminary tank, preliminary and primary will assume that 30% of the BOD has been removed. So that even though the concentration of these are the initial BOD, yeah, that's why you have to times with 0.7, because 30% of the BOD has been removed during primary and preliminary stages. Yeah, so 175 is the remaining BOD to be treated in the secondary tank, which is the BOD removal tank. Okay, so total BOD to be removed. Still, even though you have times with you have multiplied with 0.7, but yet not to comply with the requirement or the capacity, because in the effluent, yeah, you are still allowed to have 10 milligram of the BOD. Yeah, so that the total BOD to be removed, this is very accurate. Yeah, you know why? Because in the previous design we have never considered the BOD remaining, yeah, in the effluent after the treatment. But in this case, yeah, you can see carefully that 175 is the remaining BOD to be treated, but still we have to minus with 10, because 10 is the allowable BOD, yeah, after the treatment. Okay, so the actual BOD to be treated in this case is equal to 165 milligram per liter. Okay, then calculate for BOD loading rate is equal to flow rate times BOD concentration. The flow rate is 10, BOD concentration is 165. So these are the BOD loading rate. Any question? Do you have any question?
No, doctor.
Okay, great.
No, doctor.
All right, next, you continue with the calculation. Then design a two SIM. Okay, then you determine the carrier surface rate. Yeah, so take SALR equal to 6 gram per meter squared day. Okay, where do I get this value? From here. Okay, 6 gram. So okay, carrier surface area is equal to BOD loading rate divided by surface aeration loading rate. So 1650 divided by 6, you will get carrier surface area. Okay, next, you calculate for the media volume. Media volume is equal to carrier surface area divided by media specific surface. Yeah? So the specific surface normally standard given by the manufacturer. Yeah, this is part of the spec. Yeah, we can actually request the specific area that we would like to have. Maybe if we would like to conduct a study, then we can conduct a different specific area to see the to compare the process performance. So we can see to what extent that the specific area are efficient for the effective removal. So in this case, since it is a specification from the manufacturer, so it's given as 500. So carrier surface area divided by 500. So the media volume is 0.55. Yeah. Next, calculate for the volume of the removal, BOD removal tank. Yeah, so the media volume is equal to 0.55. The fill fraction in this case, they use as 50%. Just now the allowable value is between 30 to 70%. Yeah? The fill fraction is the volume of the filter media which is loaded into the tank. Yeah? So in this case, it is 50%, yeah, of the total working volume. So the volume tank is 1.1 meter cube. Okay, so when you know the volume, if you are given the length to width ratio, so you can come up with the sizing. But in the real design, whenever we have two systems, which is integrated in the biological treatment, especially in the biological treatment, normally we shall use the same width, for the assumption. It's good for us to use the same width, Yeah. So in this case, is equal to 1 meter. Okay, 1 meter. What do I mean by the same width? Because we have two tanks. Yeah, remember that we have another tank which is for nitrification, kan? Yeah, we have another tank which is for nitrification. So we are going to have the same width for the BOD removal tank as well as nitrification tank. That is not compulsory, but that is very much helpful, in terms of the fabrication, in terms of the design, so that we can standardize one of the section of the tank. It's almost impossible. Maybe we cannot get exactly the same tank for both BOD removal as well as nitrification, but at least at this point we can standardize the width of the tank, because we are going
Hello.
Yeah, sorry for the interruption just now. So I'm going to share my slide again. Okay. Just now. Okay. This one. Okay. Can you see my slide now? Can you hear my voice?
Yes, you
Yes.
are.
Alright. Thank you. Okay, now the media volume is equal to 0.55. Then we can proceed with the sizing of the tank, which is the BOD removal tank. So in this case, you are not given any, you has not been given any ratio of the width to the length. But as I mentioned just now, knowing the volume of the tank, you can always come up with the sizing of the for the tank. But since you are designing two tank, in the two tanks in a biological system, it's good to use the same value for the width. It's not compulsory, but it's advisable to do that. The same value for W. Because the next calculation is we are going to design for the nitrification tank. So in this case, they use D equal to 1.1 meter, H equal to 1.45 meter, W equal to 1 meter, and the length is equal to 1 meter. So the H is the length. W is sorry. In this case, the D is 1.1. The H is the total height. 1.1 plus the freeboard. That's why the freeboard is 0.35 kan. That's why the total depth or the H is equal to 1.45. The W is 1, the L is 1. Okay, next, design for the nitrification tank. Okay, for the nitrification tank, you have to be careful with the statement. The statement that given here is the initial BOD. The statement that given here is the initial BOD. For this reason, for this reason, just now you have to times with 70%. Remember, because BOD has been removed during primary and preliminary stages. Nevertheless, for nitrogen, it's almost impossible to be removed using any chemical treatment, any chemical or physical treatment. That's why the words here is, the term that they use here is entering ammonia. Entering ammonia nitrogen, which is as 40 milligram per liter. So they don't times with any removal rate, because during primary and preliminary stages, only BOD as well as total suspended solid, which has been removed, which can be removed. But nitrogen is almost impossible. So that you can take nitrogen as it is. Nevertheless, you also need to consider with you can also consider the required effluent. So 36 milligram per liter is the real ammonia nitrogen to be treated in secondary stages, which is the nitrification tank. So you calculate the ammonia nitrogen loading rate, the flow rate, times the concentration. Then this is the ammonia nitrogen loading rate to be treated. Okay. Next. Okay. Start. You have to repeat. The step. The step. First, calculate the surface area. Just now just now you have calculated the ammonia nitrogen loading rate. Then the second step is to calculate the I think I've lost the one second. Okay, number 2. Okay, now number 1 is to calculate the ammonia nitrogen loading rate. Number 2 is to calculate the carrier surface area rate. So this is where that you need to refer to the table just now, which is surface aeration. A is aeration. AEARA, aeration. I will include properly in my notes before uploaded in Putra Blast. So carrier surface area is equal to ammonia nitrogen loading divided by surface aeration loading rate. So in this case, carrier surface area is equal to 360 meters square. Okay. Then you can calculate the media volume. Yeah, the media volume is equal to carrier surface area divided by media specific surface. Yeah, so the media specific, since we are using the same types of media, both for BOD as well as nitrogen nitrification, so that the same value for the media surface specific surface, so the media volume is equal to 0.72. Yeah. Okay, then the final section is to come up with the design. Okay, design a 2 stages, yeah, MBBR. Yeah, so this is where this is the primary, yeah, the purpose, yeah, of conducting the calculation. Why? Because we would like to know the media volume. Yeah, previously we have calculated the media volume. Now knowing the media volume, we can calculate or compute the volume of the tank. So media volume divided by fill fraction, in this case also still 50%. So you will get the volume of the tank as 1.44. Yeah? So since the number is not beautiful, yeah, it's not nice, so you can take as 1.5 lah. Yeah, so you do the sizing of the tank. If you still remember the width, yeah, we maintain the width as 1 meter. Yeah, the same, yeah, for the BOD removal, both for BOD removal tank as well as nitrification tank. Okay, okay, up to this point, do you have any question? Okay, do you have any question? No question, yeah. I think this one is okay lah, not too difficult, yeah. Okay, the final part is to design the secondary clarifier. Yeah, remember that in MBBR system we do have a secondary clarifier just now, which is this one. Okay, secondary clarifier. So the function of having secondary clarifier is to allow the settlement of the inert material. Sometimes during biological process, the sludge production or the inert material, the cell is quite significant. So that's why secondary clarifier is required. So in order to calculate for the secondary clarifier or sedimentation tank, yeah. So clarifier, normally when we mention clarifier, yeah, we shall use the unit, the formula of the circle, yeah, circle clarifier. But in this case, we use rectangular clarifier. Is also a clarifier, but it's better known, yeah, as a sedimentation tank. Yeah. So volume, to calculate for the volume, flow rate times HRT. So normally the HRT for the clarifier for the MBBR is about 8 hours. If I'm not mistaken, 8 hours to 12 hours. Yeah, so you can choose either 8 to 12. So flow rate divided by 24 times 8. 24 here because I think the flow rate is meter cube per day. Yeah? So that because H here, because hour here, HRT here in the unit of hours, to standardize the unit, you have to cancel out day and hour. So you have to divide with 24. So the volume of the secondary clarifier is equal to 3.5 meter cube. Okay, knowing this value, which is the volume, then only you have to be careful reading the question. Yeah, whether you are being asked to design for the circular clarifier or you are being asked to design for a rectangular clarifier. Then only you can do the proper sizing for the clarifier. Yeah, in this case, I don't think that I have to show you the example because we have both example for rectangular clarifier as well as the circular clarifier. Yeah? For the circular, you have to use the formula for circle, but for rectangular, only length and the width. Yeah? So I think that's all. Do you have any question? Do you have any question for the test on Wednesday? Well, on Wednesday or Thursday? Okay. Alright, if there is no further question, I think that's all for today. Yeah, I would like to give you the more time, yeah, for you to do the revision. Yeah, I know that all of you just come back from a long holiday, and some of us, yeah, still in the blues, yeah, still in the holiday blues, yeah. So please wake up, yeah. You are having tests on the day after tomorrow. I think that's all. On next Monday, we don't have class, because our lecture on Tuesday, but there is a public holiday. So I would like to take this opportunity to congratulate a few of our friends here who are celebrating Wesak. So congratulations. So thank you everyone for your time. So don't forget to fill up the attendance. So have a pleasant afternoon. Bye.
All right. Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you, Doctor.